we're running through the introduction, the aim of the project, the wine data set description, our problem identification, the data analysis, exploration, and visualization we carried out, our findings and discoveries, as well as the machine learning models we built. Okay, so the data set was created by Paul Carters, and it contains 11 input variables based on the physiochemical properties of red wine. Some of it are listed on the screen: fixed acidity, volatile acidity, and the rest. So we're faced with the problem statement, which was that in Nigerian restaurants was currently having an issue with quickly distinguishing wine by quality. So they reached out to us to come up with a model that will help them quickly identify high quality wine. So our aim was to determine which physiochemical properties make red wine good by various methods which we used. Okay, so this was basically what the data set contains: the input variables or the features. This was what it was, basically things that you could search online and find how they affect red wine on your own if you want to. So we started with identifying the problem for what it was. We saw that the data set was relatively small and it had 11 input features and one output feature. Then we also noticed the output features contain 6 unique integers, like within the range of 3 to 8. So looking at the fact that it had just one output column and it also contained multiple variables within the output column that was more than 2, it means the problem is a multi-class classification problem. So we also identified that there was a imbalanced distribution between the values of the outputs, like the quality scores of each samples. So we identified that 5 and 6, there were very high scores of 5 and 6 as shown on the screen, while values like scores of 3, 4, 7, and 8 were very, very low relatively compared to 5 and 6. So we saw that the data set was an imbalanced data set. So we identified the problem as a multi-class classification problem with an imbalanced data set. And that really helped us to chart out a course on like how we could proceed with our solution. So we started out our methods of carrying out the projects were basically in 3 stages. The first stage was the problem identification. The second stage involved the data analysis, the exploration, and visualization. So we first of all went through the entire data sets for to do some basic cleaning. We found out that there was no missing values present in the data set. Also identified that all the variables contained in every column were of the type of float or the integer being the output column for the quality scores. And we basically discovered that there was actually no cleaning to be done because data set was actually well ordered as well. So I looking into the way the understanding the way machine learning models or machine learning algorithms work. I saw that we saw that there was a need to do some feature creation because we are given a tip in our data sets that values higher than 6.5 could be classified as good wine. So taking that into account, we basically created a new output feature from the out of the quality column. We assigned values of 0 for wines that had scores less than 6.5 and gave the ones with scores at 6.5 or above 1. Of course, there was no score of 6.5 there. There was just 3, 4, 5, 6, 7. So basically, values of 7 and 8 fell under a verdict of 1, which signified good, and the rest fell under the verdict of 0. So we proceeded to carry out exploration on our data sets. So we did that by using the dot core method on the data set for the Panda data set. We checked the correlations of the entire data set and also the correlation of the input variables to the quality score and also the input variable to the verdict score. We also checked the mean and the variance. So we compared the mean and the variance of the input variables, and we also did the description function on the data set to check the count, mean, standard deviation, and other values, just to see how the values were distributed among each, as well as how they affected the quality scores. So we also what we also did was we extracted a new data frame from the original data set, which we named as good data. That data frame contained just values with a verdict score of 1, which were like they had like just quality scores of 7 and 8. So we looked at that too to check for the correlation within that specific data set as well. Part of the visualization we did was to create a count plot that showed us the the distribution of the quantity scores as well as the distribution of the verdict scores. It clearly showed us an imbalanced distribution. And we also did a box plot of each variable and each input variable, as well as the histogram and a scatter plot metrics for the variable to see how the scatter plot was to match how various features related to each other, and as well as the heat maps and the cluster maps to identify related features and correlations, as well as their relations to how they affect the quality scores, whether it was an inverse nature or a positive or a direct nature. So these were some of the histogram plots for each variable. I think this was the box plot for each input variable as well. Um, so at the end of our exploration and visualization, we found out our findings was that there were some correlations between some input variables, such as total sulfur dioxide and free sulfur dioxide, because those two were, if you look at it, free sulfur dioxide is like a subset of the total sulfur dioxide, so they were obviously related. Then there was one between fixed acidity and citric acid, as well as chloride and sulfates and pH and alcohol. pH and alcohol was another obvious one because obviously the higher the acidity, the lower the pH. So we found out there was actually no obvious standout in influencing input variable on the quality scores of the wine samples, even though alcohol and volatile acidity showed a highest that's direct for alcohol and the indirect for the volatile acidity. So they had the highest correlation factor to the quality scores. It's our visualization also confirmed that the data set was imbalanced, like I mentioned above. Then we noticed the huge variance between the distribution of the scores of various samples under the differences between the each input variables for each sample. We saw like for instance in the total sulfur dioxide, we're having some values of like 50 or something at starters, then ended up having over 200 and something for some samples. And the same was also for free sulfur dioxide. So those two had like a very high variance, while we saw features like density have a very low variance in the values for each samples. They also noticed that there was like the scores for the total and free sulfur dioxide, also there were also like huge numbers, while for most of the other input features like the density, the chlorine, they were actually the chloride, sorry, they were actually very low, like in 0 points. So we looked at it that it could pose a problem to the accuracies of our model when we calculate feature importance. So we took note of that as well, and we proceeded to the next stage. So the third stage was machine learning, building models. We started out with data processing, which we splitted the data sets into three variables, the X, Y, and Z. the X contained all the values of the input variable. Then we gave Y the values contained in the quality colon, the quality output variable, and Z was for the verdict output variable. So the reason we did this was to have an idea of how well our model performed for the problem when it was in a multi-class in its original stage, which was a multi-class classification problem, and also when we're using the verdict scores as a single output variable. So that made it kind of like a binary classification because it just had just one and zero, just two variables within them. So that was what we did. So for to try and fix, we actually, okay, this wasn't mentioned here, but we used we used the train test. Okay, it was mentioned train test function to split the data sets into two groups. The first group, like I mentioned, had like X and Y as the input and output variables, while the second one had X and Z as the input and output variable. Um, okay, so to attempt to fix the imbalanced nature of our data set, we looked at the total number of samples in the data set. Like I said earlier, it was relatively small. So there are usually like we have like two choices to make to fix the imbalanced data set. We had like the smooth oversampling technique and the random undersampling. So we chose the smooth because the data set was small and we felt that would be better. Um, after we did this, we noticed an increase in the total number of samples for our training data sets because we applied the smooth oversampling technique to the training data set alone. So we noticed there was like an increase of, I think, 600. Yeah, we went from like 1,200 to 1,800 after the smooth oversampling. So after that, we applied feature scaling to fix what I mentioned previously as well, the high nature of input variables like total sulfur dioxide and free sulfur dioxide. So it won't really have much of an effect when we're calculating future importance. We did it by, we chose regularization. So to put each variable or to put every variables within the range of -1 and 0. And with this, we're done with pre-processing our data, and we proceeded to building our machine learning models. So we chose 5 models to carry out we chose to build 5 models, the logistic regression, the simple vector machine, and the other ones as you can see here. And we used 5 means of evaluating those models, 5 matrices to be precise: the accuracy score, the F1 score, a confusion matrix, the mean absolute error score, as well as the classification report. So we also carried out future selection on each of the models by using the QF properties of the models like regression, logistic regressions, the SVM, linear SVM, as well as the SVM, SVC models. Then for the decision tree and the random trees, we calculated the future importance by checking the future importance properties of the both of them, and we then allocated them. We allocated the scores we created a data set that allocated the scores for each of them, showing how each input variable had an effect on the the chosen output variable. So we found out that which correlated to what we discovered from the exploration, that the alcohol and volatile acidity scored highest in terms of influencing factor, influencing power on the quality score of each sample. And we also noticed the density, sulfates, total sulfur dioxide, citric acid, and chloride they also had like a relatively okay influence as well. I think the futures actually, if we're to be general, I would say there was no standout, but this was just the performance of it. So on our performance review and findings for the machine learning, we found out the models generally had higher metric scores when fitted with the data set group whose output variable was the verdict column. That was the one that had just a score of 1 and 0. When compared to the data sets group that the output variable was the quality column, which was like 3 to 8. So this was the scores for the first data set group. That's the one with output column of the verdict scores of 0 and 1. The same simple vector machine performed highest with 0.92. Though I think there was a bit of an overfit into the data set. The random forest classifier did 0.88. Decision tree was close by, and as well as the logistic regression model, and the simple vector machine linear SVC model. And for the second data set group, the random forest classifier performed best with an accuracy score of 0.73 and an F1 score of 0.72, followed by the decision tree model, then the logistic regressions, the SVC model, and the linear SVC model. The SVC model actually performed worst, which was like reverse of the case of the first one, which it performed best. So what we came to conclusion was for the data sets that was in the format of a binary classification, that was using the output, the verdict scores as a single output feature, the SVC model performed best, followed by the random and the decision tree. But when evaluating the models in its original state, the random forest model performed best, followed by the decision tree. So additionally, when evaluating our models, we checked them for the ability to predict red wine accuracy. Sorry, I'm running a bit on time, but we checked for the ability to predict good wine accurately from the confusion metrics. This was not showed here. Maybe later on I'll show you. I'll change the screen and I'll show you. So it showed from comparing all the models, the random forest models made the highest amount of prediction. I think this was actually the random maybe it got it wrong for the presentation, but for prediction, the random forest models made 23 predictions out of 25. It was actually 25 predictions out of 30 good wine samples, followed by the decision tree, which also made 25 correct predictions. Then the SVC model had 18 correct predictions out of 30, which was a bit confusing because it had like the highest accuracy scores. And when we checked it, it's also performed best when it came to predicting the wine that fell into the category of 0, which was like below, that was not actually good. So we attributed that to the data set actually being small and not having a definite result based on that. After we also tried improving our models accuracy with grid search CV and cross-validation. The grid search didn't really have much of an effect on the logistic regression and the simple vector machine. But when we used it on the simple vector machine linear SVC model, but when you used it on the SVM machine SVC model, we noticed a jump in its accuracy score from 0.8, then it jumped to 0.92. So we couldn't use it for the random forest and the decision tree, but we applied cross validation to every model, and after that the SVC model still had 0.97 accuracy, which was the highest. The random forest had 0.93, decision tree had 0.9 approximately. Then the logistic regression model and the linear SVC model had the same scores. So what we noticed was in performance, the logistic regression and the linear SVC model had similar performance for the model, for the data sets, for identifying accurate quality scores. The random forest model and the decision trees performed better, while for making when it came to the prediction of whether a wine was good or not, the SVC um, performed highest. Okay, so in conclusion, what we from the exploration we did and from the results we got from our machine learning models, we were able to um, trim down the features down to 6 from 11 of the ones which had like the most influencing powers on the quality score. So we ended up with alcohol percentage, the volatile acidity, sulfates, total sulfur dioxide, citric acid, chloride. And we were able to also estimate a specific range in which any good wine will fall within for each of those 6 features. The pH level, the residual sugars, density, fixed acidity, they all had like a large range across brands. Like when we checked the maximum range for the maximum fixed acidity value for the normal data set as well as for the good data set, there wasn't really much difference between them. So it could fall anywhere basically for them. So they weren't really useful in pinpointing whether a wine was good or not. And like I mentioned before, the free sulfur dioxide was is basically a subset of the total sulfur dioxide. So it didn't really matter. The last slide, because we're like rushing when we're trying to submit. The last slide was supposed to contain a recommendation as well as the difficulties we encountered. So the difficulties we encountered was that the data set was actually small. So it was actually small. That was number one. And number two was it wasn't diverse. It was gotten from a particular manufacturer, the Verdi Portuguese wine. So basically we couldn't use the model to predict quality scores of um, other manufacturers or other thousands of wines available out there. So the models we created were restricted to our data sets, and even even though it was restricted, it was only applicable to that specific brand to an extent because, like I mentioned, the data set was small. And then the also another problem we faced was the data set was imbalanced, which we used the smooth oversampling technique to try and fix that a bit. And for the recommendation, I would actually give 2 models to the Nigerian restaurants, the SVC, the simple vector machine SVC models, because I believe it had the highest accuracy score. So I believe they could easily, quickly show which wines were good, which wines were not, which wines are good, which wines are not good. So if they are trying to like, okay, we're trying to get all quality wines, you can get quality wines for different prices. It doesn't necessarily mean like if you are buying a quality wine, it has to be high priced or overpriced. So you can get for different price ranges. So it easily choose between brands which one is, or choose between samples which one is good or not. Then when you are trying to like get an accurate um quality score, would recommend you use the random forest model because it shows the best performance for predicting quality scores of the wine. That way, when they are trying to get the cheaper ones, they won't necessarily they will be sure, okay, the quality is 6, which shows, okay, 6 or 5, that's like normal range. So they will look at it, okay, 6 or 5 is normal range, we can get this for the customers that want to spend less money on their wine, but not necessarily compromising on the quality. So that way they can easily make the decision. But for the quick, whether this wine is good, whether this wine is bad, when they are ordering on batch, the SVC model will be best. So I will also recommend them to get a bigger data set and also a more diverse data set for us to build them a more comprehensive model which they could use to check through different wine manufacturers or different wine brands with more higher accuracy and like a more generalized model essentially. So that was basically it. Thank you. I think I took too much time.
Okay, hold on this slide, please.
This
Thank you,
slide.
children. This slide, yeah, this particular slide.
Okay.
Thank you very much, Chizaram.
Yeah.
Chizaram, yeah.
Chizaram, yeah.
Okay,
That was a great presentation.
Yeah.
I just wanted to make one comment. Sorry, one moment. Okay, yeah. So I think you meant support vector machine, not simple vector machine.
Oh yeah. Yeah.
Yeah, I was confused for a while. I had to Google to make sure that there's nothing called simple vector machine. So,
Yes.
so please update your slide with
Yeah.
correct terminology.
Yeah.
Yeah, and I like the fact that you checked for the quality in terms of like doing both binary classification and then the other one was that was linear regression, right? Because you were looking at the quality score. Or
Yeah,
did
the
you?
multi-class classification.
Oh, you treated this as a multi-class
Multi-class, yeah.
classification. That's okay. Okay. All right. I mean, yeah, that was really great intuition. Well done.
Thank you.
I don't have a question for you. I just wanted to say well done.
Okay.
Thank you.
Before we move on, I just want to announce that Ibrahim is on the call. So for those of us that don't know Ibrahim is also a part of the AI Saturdays. He's the one in charge of, so for those of us who signed up for the newsletter, Ibrahim is the one responsible for it and everything media and AI Saturdays. So please, let's welcome Ibrahim. You don't need to unmute, just stay mute here. Welcome him there. Welcome, Ibrahim. Okay, so we started with Emma the other time. Maybe George should go first this time around. George.
Hello. Yes. Yeah. So personally, this is a wonderful presentation. Yeah, I must say that. Why? Because I think you followed like the proper machine learning practice. Like you did like everything, not necessarily like everything. Like you did the fundamental things. So let me just highlight the one I kind of found interesting. The feature engineering stuff was kind of cool. Like I like that part of increase you considered like one that are greater than 6.5. You created a new feature for it. You regarded it as good. I think that one is cool. Your data exploratory process was actually, I like that too. Then, yeah, I also have like a question. Like, did you normalize your data?
Oh, no, I didn't use. I just used regular standardization, sorry, rather than
Okay.
normalization. Yeah.
That's what do you mean by it's just to use? That's normalization, right?
Yeah, that's actually, yeah.
Oh, okay.
That's,
Okay.
yeah.
Then I like the regularization part too. I think that's also cool. Model evaluation, like everything is just on point, apart from your time management in presentation.
Yeah.
Then also there's something I want to like I want you to kind of improve on. Can you go back to that slide whereby you have plots, the slide with plots? Yes, so like it will make sense when you present a plot, you should have like in a text explaining what the plot is about. So like, yeah, I don't know what, yeah, it's cool, but still I want to like know what this plot is about. And also you don't necessarily have to like, squeeze all your stuff in one place. You can just move them around, like make it visible so people will know that you put so much effort in doing this stuff. So
Okay.
personally, everything is actually on point here.
Right.
Nice
Thank
one.
you. Yeah, thanks.
And also, yeah, true. I have another question. I forgot to ask this question. How about combining your models? Like, do you think like maybe model ensembling, like combining those models, do you think it will give you a better result?
Like combining two different machine learning models.
Yeah.
Yeah, I think it might actually have like a good I actually don't know how to do that, but I think it should like maybe combining something like the random forest and the um SVC model, like taking the best of each and get like a better um model. I think it should work.
Just yeah. All right. Thanks.
All right. Thank you.
Thank you, George. Okay, so let's go Ikechukwu. Is Ikechukwu on the call? Ikechukwu.
Maybe went to get wine.
Okay, Udeme, let's go Udeme. Udeme.
Yeah. So, she's a room, nice one. In fact, when you were going through all of this, my head was just like, I want to see your code. Yeah, basically, like I would have really loved to see your code because even like your features are, I mean, there are loads of outliers. I mean, from your feature, from what I can see from here. So, like the first thing that I wrote down here was, okay, although while you were going, you kind of answered some of them. I wrote like the imbalance data set, what did you do? And then the outliers, how did you handle it? But then you did the standard, you use the standard scaler to try to normalize your data and stuff like that. And then the imbalance data, quick question. So you kind of did a multi-class classification and a binary
Okay.
classification. Yeah.
Yeah.
So for the imbalanced data set with regards to the classes, like the class labels, did
Yeah.
you actually, like, how were you able to fix that? I know you said you use like smooth over sampling, but did you do it on both of them, or you actually did for the one that you worked with, like the binary classification? Did you
Yeah,
also
I did it for both of them. I did it for both of them.
Okay.
Yeah, and I noticed the total number increased like by 600 from 122, but I did really check um the distribution to see like how the values changed afterwards. That was something I think. But I just
Yeah.
assumed okay, probably it would be much better like afterwards.
Well, yeah, because me, like I said, when you were going through it, I was really interested in your code because, I mean, there are lots of stuff that can actually make your model to be a little bit biased because of the distribution of the classes.
Yeah.
Yeah, so I was really much interested in like how were you able to ensure that you made your classes a bit balanced to an extent, in as much as it was like totally, like you said, random. And then you also mentioned stuff that the data set was quite small. Well, I wouldn't really think it was quite small though. Yeah, I mean, I don't know, maybe you were expecting like 10,000
Yeah.
data set and stuff like that. Yeah, but even sometimes, like in real life scenario, although more data makes things better, but in real life scenario, sometimes when you're trying to like get data to solve a particular problem, sometimes you just have like very little data sets, and then you just have to randomize and try to make more data out of the small data you have if you think the data set is really small.
Okay.
Do you get? But yeah, nice one. And well, the presentation was really great. It kind of felt like I was in a beginner class that I was being taught what mean and median. You said you did the dot describe, which is quite cool, but it was like a lot more detail, which I would think that in a like maybe in your next presentation, you might just try to short circuit all of those like really, really detailed stuff. Like I did dot describe to check the mean, the count, and all of that.
Yeah. Yeah.
Yeah.
Thank you.
Well done.
Yeah, I actually think that in this way, in this setting, it's good because that's basically the machine learning and data science class. It's meant to go as detail as we can. If it was that the deep learning student now, I would say, of course, like we learned this in machine learning, we know what that describes does and all. But yeah, I understand the main points because it's a boss, you know. But I think it was great for a lot of people who probably don't understand that what the terminologies means, or people who in the future might just be stumble upon this video online and feel like, oh yeah, I didn't know what this means, and it could be useful to them. So yeah, thank you for going in depth.
Yeah.
Yeah, great.
Yeah.
Okay, great one, nice one. Ikechukwu, are you back?
Oh, yes, I am. Nice one, Chizroom.
Yeah.
But there's a fundamental principle I just want you to take note of. In presentation, they say show, don't tell.
Okay.
Show people what it is that sometimes some of this, the reason why you had a lot of text in your presentation, people will easily get lost when following the presentation. Maybe like the place where you say you did dot described, you could just show us a table, an image of that and stuff like that, then you explain it to us and it would have been more catchy, I would say. Then your process was quite detailed, but it's important that you keep track with what actual business problem you're trying to solve. Because yes, you was it a problem? Was the restaurant concerned about rating wine to determine pricing, or were they concerned with determining which is good wine so that they don't serve their customers bad wine?
Yeah.
Because
The reason for that was actually like in the problem statements or in the work we were given, the description for the project. Part of the description was finding which physiochemical properties made red wine good. That was from the project standpoint. Then from the restaurant standpoint, they were trying to find, they needed a model to predict which wine was good or not. Like, so I did
so what I'm trying to say is that, remember, the actual idea behind machine learning and all this process we're going through is not, machine learning doesn't make any sense if it doesn't have business application. So at the end of the day, I just want you to have that in mind. It's not like what you did is great, because I understand where you're coming from, but just have that in mind. The idea is the business application. So
Okay.
and in that sense, you would understand that actually doing that binary classification would have actually been great. But also in your metric, in making your recommendation, you use the accuracy as a basis for making your recommendation. Maybe I wouldn't have done that, because if, especially in the binary case, let's say the restaurant wants to know what is, they have, let's say for a premium restaurant, for example, and they wanted to be absolutely sure that this wine is good before they serve it to their customers. It will now be important for your model not to predict bad wine as good wine, which means false positive.
Yeah.
So in that case, the accuracy of the model might be good, but if you have a lot of false positive, it wouldn't help the business, because it means that your model, even though very accurate, still predicts a lot of bad wine as good wine. So
Yeah.
at the end of the day, it doesn't help the business achieve its purpose. So really, the metric you use in looking at at your model is determined to a large extent by what kind of business problem you're having. So just have that one in mind. But also remember, this is analytics. You should show your superpower as somebody that is into analytics, machine learning, and stuff like this. So show more charts in a presentation, because people even prefer that, because people can get lost in text. That's what I would say about the presentation. But all in all good. Kudos.
Noted. Thank you very much.
That was a really great feedback IK, I thought about the same when I was listening to you. Even though I appreciated the text and all and listening to you, I didn't read most of what was going on. And I was like, when do we get to see chat? But yes, to be honest, you need to be able to show more chats. I also had this thinking from Udemy, like I would like to see the code. I'm not even sure if you're telling me the truth or not. So you just like wrote a lot of text, and I'm like, oh yeah, this is great, this is great. But I can't see the chat, and I don't have the code, so I might question it a
Yeah.
little bit. But I know you did the work, for just a good feedback. You should try to put a lot more chats. That shows that kind of like speaks for itself, just like Ike said.
All
And
right, no problem.
yeah, thank you so much.
Yep.
Yeah, so sorry, one more from my end. I think your last slide where you kind of showed the different score ranges for the different variables that you thought was that your model actually said was necessary. No, no, not
Last
this,
slide.
not like the accuracy score. The range is this. So how were you able to come up with these percentages?
Okay, yeah. So I said I extracted the data frame from the original data frame. I called it good data. So that data frame I extracted had like all the samples there were of good nature, or for 7 or 8 quality score higher. So I checked their minimum. Took a look at the minimum values for the good uh, um, the samples that had good scores. I looked at the minimum value, then I put that down as for each each of these features. Some of them had a direct relationship with the quality score. Like when they increase, the quality will increase. Then the volatile acidity had an um, inverse relationship. So when as long as it decreases, it's when it decreases, the quality score increases. So for like features like the alcohol, I looked at the data, the extracted data sets. I took the minimum range, like the lowest score value for alcohol percentage. Then I went to the standard data frame, and I took the highest from the standard data frame. So 14.9 was the highest any sample scored for alcohol. But for the samples that actually rated good in quality as well as the verdicts, the lowest was 9.2. So I did the same for volatile acidity. Instead of I looked at the data set of the good wines. I took the highest value for the volatile acidity, that because like that's how I said it has an inverse relationship as it reduces, the quality increases. So I took the highest, then I went to the normal data set and I got the lowest value. So that's how I was able to balance kind of the estimation.
Well, I think I became more confused anyways. Um, yeah, but does this mean that these scores are not like without you training a machine learning model, these scores will still be the same?
Yeah, generally I think so, because the more volatile um a sample is, like, I think this part of the reason the project interested me was I actually like red wine. But the more volatile it is, that means it's like when you look at the methylated spirit, it's very, very volatile. Once you open it, some of it can evaporate. So for your alcohol, you won't really want it to be volatile. You don't really want it to have a high percentage of volatile acidity. You want it more stable, something you can hold down. Like I
So
think
these are
everybody.
like standards, like these are
Standards, yeah,
standards.
yeah, these are standards, yeah.
Okay, because from the result, it was looking like it was one of the insights you got from, your machine learning, and then from the training and all the insights you got, you're able to come out with this. But I
Yeah,
guess
I correlated them with real value influences as well. So they both matched up.
Oh, sorry. The way I understood this data, please correct me if I'm wrong. is that after you use the models to train the model to get the quality, you looked at the ones that had higher quality, and then you check the data set to see what's the range of like good wine falls. Is that what you did, or?
No, for like the for evaluating which the ranking of the input features, that's the physiochemical properties. I used feature importance and the QF property to find scores of like how each feature performed relative to their influence of on the quality scores or the output scores. So this were like the ranking of when I looked at each of the model. I did that for every model. Then I made like an estimation and came up with like um an overall ranking. So this is like the overall ranking of the machine learning future importance. So what I just did was I brought it down to 2 with like future selection, down to 6 from 11, and then I disregarded some of them when I looked at their values, which I put down. So it was actually based on the ranking on the future importance.
Okay.
Thank you very much. I think we've spent 1 hour. Thank you.